A very good morning to everyone, and this is the third chapter in the series of Bio 101 topics, and this involves talking about water, not just its chemical properties, also how it is relevant to sustaining life on Earth, and that's what we are going to be talking about today. Okay, so there are some things that you need to walk away with at the end of this chapter, and those are listed here. Okay, so you need to know the structure. You need to know how it forms the hydrogen bonds. You also need to know the 4 important emergent properties of water. Okay, because of the ability to form these bonds, and so how is it relevant to life on Earth? Then you need to get an idea about what is hydrophobic, hydrophilic, what is a solute, what is a solvent, what is a solution, how you calculate molarity. If need be, we'll be talking a little bit about that. And then what is an acid, what is a base, what is pH, what are buffers, what is acid rain, what is acidification, and what is the status of coral reefs today on Earth. Okay. And as you can see, this is a picture of the Earth from outer space, and you can see most of it is blue. And we all know this, more than 70% of the Earth's surface is covered with water, and we should consider ourselves fortunate, lucky, and that is the main reason that helps us sustain life on Earth, and also in many ways that is what helps us continue to live, thrive. Let's see what happens. This is like an aerial photograph of the surface of Mars and the planet Mars. And as you can see, this they detected ice in Mars, which means they have this suspicion that once upon a time there was life in Mars, and we'll see what happens now. Next. Okay, so here's the thing. We already in the previous chapter talked about the different kinds of bonds, like covalent bonds. Then we talked about ionic bonds. Now this was very strong. This is reasonably strong except when it is in water. And then we talked about hydrogen bonds. So we sort of go over the property of hydrogen bonds one more time in this to help us understand what it is and how it is helping us maintain water, or not helping us, or helping the water to stay liquid, and the different states of water. Okay, so here's the thing. Water is composed of H2O, meaning 1 oxygen molecule and 2 hydrogen molecules. As you know, the valency of oxygen is 2, means it has a requirement of 2 electrons in its outer orbital in order to achieve stability. So this in here is the inner orbital, the first orbital, which has 2 electrons, and then 3, 4, 5, 6, 7, 8. So oxygen has 8 electrons, of which 2 of them are already put into the first orbital. In the second orbital, there is only 6 that can be put, which means it leaves behind a space wanting for some electrons, and so it is reactive. It is capable of reacting with different chemicals to somehow or the other get electrons to fill this spot and to achieve stability. Now, the story of hydrogen here. Hydrogen, has one electron and one proton. It does not have any neutrons. Okay, so it has only the first orbital to deal with and just one electron, and it needs one more electron to complete its orbital and maintain stability, achieve stability. So what happens is it readily combines with oxygen. So how you end up having that is this here is your oxygen, and it has a requirement of one electron which is satisfied by one hydrogen and requirement of another hydrogen with bonding with the same oxygen. Now, things would have been just as is, and we wouldn't really be talking about it if things just stayed as it is and everyone respected their contract of equal sharing. But that is not to be. Why? Oxygen is very, very electronegative. Okay, which means it attracts electrons towards itself, which means it really does not wish to part with the electron once it has them. And poor hydrogen, what will it do? It is not as strong, it is weak, and it cannot fight against the strong oxygen. So it sort of gives in and waits that and hopes that sometime or the other it might get a chance to get one more electron towards itself and complete its orbital. So it stays put in this particular marriage or marriage of three individuals. That's silly, but so what happens is these two electrons from the hydrogen end up giving oxygen a slightly extra negative charge, whereas on the hydrogen side of the water molecule it has a slight positive charge, very, very slight, and that is why it is represented with a delta plus. Okay, this sort of gives it polarity, a polar nature or a polar nature. And so what is the outcome of that? So here, this here is one water molecule with all its charge and everything, and this here is another water molecule, right? Now the hydrogen of this water molecule, has a slight positive charge and shows attraction towards the oxygen of the other water molecule. So this is one water molecule, this is the second water molecule. So the hydrogen of one water molecule is attracted towards the oxygen of the other water molecule or neighboring water molecule, leading to a transient attraction, which is there but not there. Okay, so it sort of exists for a very, very short period of time. But if there are millions and millions and millions of water molecules, all of them get attracted at a certain point, and then the bond makes and breaks. makes and breaks. The bond exists for 1/1000th of a second. Okay, which is what gives you this hydrogen bond. I have noticed a lot of students, when asked what is a hydrogen bond as a definition, a bond between oxygen and hydrogen, that is not good enough. Or bond, just a bond with hydrogen is hydrogen bond, that is not good enough. You have to be very, very clear and explain that the bond between the hydrogen of one water molecule with the oxygen of the neighboring water molecule, because of their transient charges that are present, their polar nature that it exists as, that is the hydrogen bond. Okay. So this is another way of expressing the whole process one more time. And you have, because of that, water has 4 emergent properties. Now these 4 emergent properties, I have listed them out as a mnemonic to remember facts. Okay, they might not be listed here in the same order, but all the properties are listed along with this mnemonic. It's a very easy way to remember all the 4 properties of water, which helps in sustaining life on earth. So the first one we are talking about is cohesion. Okay, now in order to understand cohesion, you have to think about, say, a chain, or say, if in your childhood you have had these magnets and steel balls that you would play with and build stuff. Okay, and with that, I normally in class I would just bring that and I would show you that it sort of is able to hold on its own and stay straight above the ground, above against gravity, kind of like this. They stay up. All of that is because they are attracted to each other. And similarly, your water molecule, one water molecule, H2O, is attracted to the water molecule above it, and that above it, and that above it. And that sort of makes it move against gravity in these xylem vessels of plants, trees. So from the root to the leaf, water is able to reach these parts, spaces, because of the property of cohesion. In addition to this, okay, in addition to this, there is another property called adhesion. Adhesion is, now cohesion is one water molecule attracted to another water molecule. Okay, whereas in adhesion, on the other hand, one water molecule attracted to the walls of the xylem vessel of the plant, okay, the cellulose part of it, and moves. For this, I would like for you to imagine if there is a rock climber, okay, what he does is basically, if he is right here, in order for him to go up, he sort of holds on to one part and pulls himself up. Okay, and then again he holds on to the side and pulls himself up. So that holding on to the side of the wall for grip, for some amount of force with which he can pull his entire weight of body upwards. That kind of process is seen when water molecule sort of gets attracted to the walls of cellulose of the plant or the tree and helps move up against gravity. And adhesion and cohesion together help water move from the root to the leaf, and they are able to do this because of the polar nature of water molecule. Okay, now surface tension. In order to understand surface tension, the best way, I mean, these kind of stuff I can only tell you. Sometimes when I get a chance, I let you guys perform this in the class or in the lab. So you take a glass or a beaker and you keep filling it with water, keep filling it with water. Sometime you would have more water than what the vessel can contain, and it still stays there, it doesn't fall off. Why is that? It's basically because the line of water molecules at one level pull and hold on to the line of water molecules above that, sort of hold on to it, don't let go, which means it forms like a skin or a layer on top. This is not broken by some animals which can walk on water. So I do not know, in television sometimes you would see any of these Animal Planet kind of pictures where you can see this lizard, okay, literally walking on water or splashing over and walking on two legs on water and reaching from one end of the pool puddle of water to the other end, or even the river, so on and so forth. Or we have a water spider here in the next picture that can help you get the hang of it in a few minutes. So this particular picture explains the process of cohesion and adhesion. So this attraction which pulls one water molecule and the other water molecule up against gravity, okay, is cohesion. Okay, and adhesion is water molecule and the wall of cellulose of the plant, which is a water conducting cell like a xylem. Okay, that is adhesion for you. Okay, so the adhesive property of water also allows for formation of water droplets kind of like this, and it sort of stays and you can pick it up for some time till that surface tension is not broken. Okay, so here you have this water spider which is able to stay afloat in a body of water because it's not breaking. It has distributed its body weight in such a way that it is not breaking the surface tension of water. Okay, so how they are attracted is, supposing this is the lower layer, it sort of holds on to the upper layer and doesn't let go, like I was talking to you in 2-3 slides before. Okay, so that was C for you out of the facts. So when we have, right now I'm going to be talking about temperature moderation. Okay, in order to understand temperature moderation, I would try to take the example of, say, swimming pool and a kettle, and you have put this kettle under flame. Okay, so this is your kettle for you. Now tell me, if you put the kettle with water, okay, let's put water here and heat it, and it boils. Okay, and versus the swimming pool, which is during winter is maintained at say 30 degrees centigrade. Okay, now tell me, what is the temperature of the kettle when it boils, and what is the heat? What is the temperature and what is the heat? Okay, in order to understand this is, you would say, oh, it is boiling. Now, which one is got a higher temperature? Which one is got more heat present in it? The simplest, most logical conclusion would be the temperature of the boiling water in the kettle is high. Temperature is high, but and the temperature of the swimming pool is lower in comparison to the kettle. But the amount of heat required to heat this is low, whereas the amount of heat required to maintain this at this temperature is very high. Okay. All of this goes to show that you have a big difference of the amount of heat required to maintain it at this particular temperature, whereas the amount of heat required to maintain it at a small, all logically everyone would end up saying, oh, that is because it is smaller quantity. Sure, smaller quantity, but the thing is the temperature is like 100 degrees here. Okay, so water has a very, very high specific heat. The point I'm trying to make is temperature is a very different thing from the amount of heat that is required. Okay, and water has a very, very high specific heat. It is kind of like a like one of these boxers. Okay, one of these boxers who is like, I can take it, give it to me. So you keep on heating it. Okay, he's able to take that and not fall down. Similarly, water, you keep on heating. It takes a very large amount of heat to raise the temperature of water. Okay, meaning it is got a very, very high specific heat. Okay, so another way to get an understanding on this is if you have like a saucepan and handle and you have added water to it and you are heating it up, the saucepan will get hot faster. The water when you're touching will not get as hot, not as hot, because it has a very high specific heat, and the metal container in which you keep it has a very lower specific heat as compared to water, meaning it takes more than just that much to heat water up. That's what it means. Okay, there is also another term that you need to understand with respect to temperature moderation, that is evaporative cooling. The best way to understand this is if you have gone on a jog, okay, and then you come back. So what has happened is your metabolism is very high and your body is all heated up. You can feel that heat radiating, but you start to sweat. What is the point of the sweating? The sweating is the body releases this liquid, and once that sweat dries up, it helps in bringing down the temperature of your body. So it is your body's way of trying to regulate the temperature and maintain it at homeostasis level. Okay, So water generally absorbs the heat from warm air and brings down the temperature of that warm air. Okay, basically, like you have like I can give you an example. Like when my kids were babies, I would make a bottle of milk for them. Okay, and that bottle of milk would have warm milk, and it would be really warm for them, and they cannot really drink it. So then what I would do is either I would take another vessel and pour it back, and pour it and pour it back, pour it and pour it back. What I'm basically doing is I'm like transferring all that heat of that whatever the milk contained out into this container. Similarly, what happens is if you're having a very heated kind of area and you're close to a water body, the heat emanating from that heated area goes over the water, and water absorbs all that heat, which brings down the temperature of that warm air. Kind of like when you go near the sea, even though the city was really hot, the same temperature is what is assigned to that area, but the temperature goes down, especially just near the coastal area, because water has absorbed all that heat from that warm air. All right, so it is capable of moderating the temperature. That's what I'm trying to say. So it also, another way to understand this is if you have if you're going to the seaside. Okay, if you go to the seaside and there in the day water feels cool because actually it is absorbing all the heat, but the temperature has not risen. It absorbs the heat, but temperature has not risen. Okay, it takes it an entire day for the temperature to rise, to become a little warmer. And then what happens is by nightfall the land side area is cooler and the temperature of water is warm. So like at night, if you walk by the sea, it will feel warm. The water feels warm. Excuse me. Okay, so that is to explain the moderation of temperature. Water's high specific heat can be traced to hydrogen bonding. Heat is absorbed, it absorbs and absorbs more, and then hydrogen bonds break away and water goes out away from one to the other. Okay, so if you have a container and you're heating it, so all of these water molecules are held together by hydrogen bonds. When you heat it, it is absorbing all that heat, and it absorbs it to a great extent. At a certain point, water molecules sort of break, go off into the gaseous state, right, from liquid. All right, so I would like for you to remember, when you heat it, it absorbs and absorbs and absorbs as much as possible because of its high specific heat, and then when it cannot take it anymore, it starts to break away and go off. Okay, so heat is absorbed when hydrogen bonds break, and heat is released when hydrogen bonds form. Okay, a high specific heat of water minimizes temperature fluctuations to within the limits that permit life. Now what does that mean? Supposing you take this huge big body of water, a lake, and it had this water, the temperature of land. Now you have this 1 minute huge big body of water, and this is a lake, or you can be calling it the sea or anything, a big body of water. The sun falling onto it can heat up the land. If it heats up the land and water to the same extent, what would happen is it would get very hot in the day and very cold at night. So the fishes and all the life that are present in this might have to experience a large variation, which is not really helpful in sustaining life. So the water, actually its property comes to the rescue. Okay, basically what it does is it keeps on absorbing as much as possible and does not increase in temperature as much, and does not cool the temperature as much, which helps maintain a steady temperature in the water. So it permits life to live without experiencing extreme variations. Okay. I just now spoke to you about all of this. Okay, so we move on to the next. Okay, floating of ice, the three physical states of water. Okay, when water is in the liquid form, there is a semi-ordered kind of state. It has hydrogen bonds. The bonds make and break, and it has some amount of closeness and distance between. So it can be close and it can be far from each other. It's very, very transient kind of state. When it is in vaporized or gaseous state, they are only far away, and there is no hydrogen bonds holding them. They are far away, very rarely, very few hydrogen bonds can hold. Whereas when you have frozen water, they are in a very ordered molecular structure, equidistant from each other. Kind of, just let's imagine, say, 8 molecules of water. If it is in a liquid form, these 8 fellows can be, okay, no, this was 9, say 9. Whereas if it is in the frozen form, it would be, okay, which means it occupies a specific fit kind of very, very ordered kind of structure. So it occupies a specific volume. Okay. And for example, when you have, say, some frozen soup or something, that food, frozen liquid food, the best is juice. If you freeze it, if you first of all fill it to the brim and you freeze it, when you take it out, you will see it's sort of bulging on the top, right? What does this mean? It is the same volume. Sorry, same, excuse me. It is the same mass, quantity quantity is the same. There is nothing wrong with the quantity. So the mass is the same. Okay, whereas the volume has changed, increased, whereas the volume stays at the same level as the glass. Okay, in comparison to the volume of frozen liquid, say frozen ice or juice or anything. This is like a personal experience if you have seen it. Now, density is mass upon volume. So the mass has stayed the same. With respect to a liquid, mass and volume gives you, say, a certain value, say 1 in this case. Whereas frozen ice, the mass is the same, but volume has increased. So the density is probably less than 1. Less than 1. Excuse me. Less than the value here. That's what I'm trying to say, which means it has got less density. Okay. We go over it one more time. Consider you have a glass of water and the water is filled in one beaker exactly to the brim. That is the mass of that water that you have added into the beaker. That if you freeze it and you look at it afterwards, it is sort of bulged out. Okay, so that means the mass is the same, but the volume that it occupies is more. Okay, so if you calculate the density of the liquid water versus the density of ice, you understand that ice has less density. Okay, and that is why ice floats. Okay, so when we talked about cohesion, we talked about temperature moderation. Now we are talking about floating of ice. Okay, what is the importance and significance of this? Let's see. In the winter months, okay, a water body has water and the temperature is low of the atmosphere, so it starts to freeze. Rivers and lakes and so on, they freeze the topmost layer. And below that, it stays liquid. The reason is ice floats and stays on top. So the liquid below that is able to stay as a liquid and sustain life. Otherwise, so come winter, if everything is frozen, and then come summer or say spring, if everything is frozen and that's why they died, there is no other life for the next year, next season, this cannot be. This doesn't happen. So the property of ice floating on water, because of lower density, because of ordered structure of the hydrogen bonds, okay, gives you a chance or gives life a chance to live. Okay, so here you have on this floating ice polar bear trying to search for food. He uses it for another purpose. Okay, so the last property is solvent of life. We'll go on to talk about what is a hydration shell, what is hydrophilic, what is hydrophobic, what is a solution polarity, colloid, solvent, molarity, etc. Okay. Now, again, the hydrogen bonding nature of water helps in it being a very, very important solvent. Okay. Solute is anything that can dissolve, okay, any material that can dissolve in a solvent. A solvent is something that makes stuff dissolve inside it. Okay, a solution is solute plus solvent. Okay, it's like a combination of these two guys. A colloid is like a mixture which sort of stays in suspension. It's not really completely solubilized, it stays in suspension. Milk here, for example, is a colloid. Okay, hydrophilic means liking. Philic means to like. So hydrophilic means liking water. There are substances which are hydrophilic, which means they will dissolve in water. For example, salt, it dissolves in water. Sugar, it dissolves in water. Hydrophobic, on the other hand, does not like water. It repels water. Best example would be oil and water. If you put that as a combination, oil is hydrophobic towards water. Okay, and we'll talk about the hydration shell in a minute. Okay, so imagine that you have a beaker full of water and you added some salt. Salt is sodium chloride. Okay, now sodium, as you know, okay, has 11 atomic number. So in the first orbital it has 2 electrons, in the second 3, 4, 5, 6, 7, 8, 9, 10. That leaves only 1 in the third orbital. So this makes it tough for sodium. So in order for maintaining stability, it cannot try and search for 7 other guys to donate or to share electrons with it to form a bond. It is easier for it to just give this away. Chlorine, on the other hand, okay, once again, chlorine on the other hand, okay, has atomic number of 17. So that is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17. Leaves it only one spot. So it is easier for it to just find one electron through someone. So it's highly reactive. That is a given. So sodium and chloride seems to be like one of those best fit bonds. Okay, they're just like made for each other. So they form together an ionic bond. So sodium just donates 1 electron to chlorine and chlorine just accepts 1 electron from sodium. All right. So that is the basis of the ionic bond, which is fine. When they are put in an aqueous solution, okay, this bond becomes a nothing. Okay, why? What happens? Think about it like this. I would like to say there is one guy who is who is like sort of sitting down here, and he's very, very shy in a dance hall. He's just sitting very shyly, and then there are these girls who would come. They'll say, hey, come, dance with us. So all of them hold his hand and take him. So they sort of surround him and hold his hand and take him. Think about sodium being surrounded by water molecules and taken into solution. Okay, how is that done? Sodium, because it has given away 1 electron, donated 1 electron to chlorine, it itself is positively charged. It has become a cation. Okay, and the negatively charged side of water molecules surround the positively charged sodium, and bring it into solution. This is formation of a hydration shell. On the same note, chlorine. Okay, let's see what happens to chlorine here. Chlorine, on the other hand, is negatively charged, so the positively charged side of water. Okay, bring it into solution. All right, so this is formation of a hydration shell. Okay, so here you can see a lysozyme, which is an enzyme, a protein, which is hydrophilic. Okay, it sort of has a lot of water molecules bringing it into solution. All right, forming a hydration shell. So if we move on to talk about acids or basic condition. Okay, generally what happens is one water molecule is attracted to the other water molecule. So you have two water molecules, but it is sort of like a zig and a zag, in the sense this oxygen sort of pulls this hydrogen to its side and it stays as a hydronium ion, and this stays as a hydroxide ion. Okay, but it's like a reversible reaction, so they stay in a dynamic equilibrium. Okay, now to understand a pH scale, I would say think bean bag. So you have a bean bag. You press here. What happens? All of the molecules, all the beans go to this side. You press here. All of them go to this side. But are they going out? No. Right? Similarly, you have to think about it. Pure water, okay, has a total concentration of combined concentration of the hydrogen and hydroxide ions as 10 raised to minus 14. Okay, so concentration of hydrogen in pure water at is equal, in the sense it is 10 raised to minus 7. This is 10, hydroxide is 10 raised to minus 7. Okay, both of them together come and give you 10 raised to minus 14. Now what happens is pH of any material, now pure water, okay, the pH is 7. How do you understand the pH? Okay, pH, the value or the formula, the way it's represented is minus log to the base 10 H plus. Okay, so if I have to understand the value of pH, now tell me, if I say 10 raised to minus 1, how will you represent it? You will represent it as 1 by 10, right? And you would be right. Now you have 10 raised to minus 2. How will you represent this? 1 by 100. Now tell me, 1 by 100, is it more than 1 by 10? No. 1 by 100 is lower in value as compared to 1 by 10. So though your denominator has a lesser number written, it is still of more value, higher concentration as compared to the tenfold increase or that you see. In the sense, what I am trying to get my students to understand is 10 raised to minus 1 is definitely higher in concentration as compared to 10 raised to minus 5. And why? Because 10 raised to minus 5 in actual is 1 by 100,000, 1 divided by 100,000, whereas, and the value is very, very low in comparison to this. So though it feels like a big number, it is not a greater value. That's what I'm trying to say. Okay. So, like I said about the beanbag, at pH at 25 degrees of pure water, okay, is calculated as the concentration of H and concentration of OH, which is 10 raised to minus 14. Okay, so minus log to the base 10, 10 raised to minus 7 is minus of minus 7, which is equal to 7. So pH of a neutral solution is 7. Okay, so there is a range of pH that exists for a different set of liquids. They range from the scale of 0 to 14. Okay, so battery acid being the strongest in its value, about pH 1, which means it has a lot of H plus. Okay, whereas at this particular point, oven cleaner, okay, it has very less H plus but more OH minus. Here it has a lot of H plus but less of OH minus. And at pH 7, okay, H plus and OH minus are equal in concentration. Okay, so then there are these different things that have different pH values. Can you see that gastric juice or stomach acids have a pH of 2, and urine has a pH of 6, and blood has a slightly higher pH. It is not low. Be aware of that. Okay. So then, depending on whether you have more of H plus or more of H plus or less of H plus, you can be either an acid or a base. Acids generally increase the concentration of H plus. Bases or alkalis reduce the concentration of H plus. Neutral solutions have equal concentration of H and OH. Acidic and basic conditions affect the living organisms. Okay? A strong acid has an unidirectional dissociation. What he means by that is HCl dissociates, and the arrow is like just a single pointed arrow. It doesn't go back and forth, not reversible. H plus plus Cl minus. Okay, same way with NaOH, sodium hydroxide, Na plus plus OH minus. Whereas a weak acid, it would be reversible. H2CO3, okay, H2CO3 is H plus plus HCO3 minus. It sort of is a reversible reaction. Same way with the weak basis of ammonium hydroxide. Okay. Now, what is a buffer? A buffer is something that maintains the pH. A lot of students understand this as bringing the pH to neutral. No. No, that is not true. Okay? It maintains the pH to what it should be. Like for example, your blood pH should be 7.4 all the time. Okay, that's the way it is. Now, if for some reason you consumed a lot of acid and suddenly the pH of the blood has decreased further to say 7, this is extremely dangerous for the body. So there are buffers which would maintain the pH to this value and not let it change. On the same note, supposing you have consumed some alkali and the pH has risen to 8, then there are buffers which would bring it back and maintain the pH to 7.4. Okay, so how does this happen? H2CO3, which is a weak acid, what happens is it is capable of donating H plus or hydrogen ions if there is a rise in pH. Rise in pH means alkaline, right? It becomes alkaline. So it wants to add H plus to bring it back. Okay, so the reaction will go in the forward direction, kind of like this. Okay, on the other hand, if there is a drop in pH, what they would do is, that means it is becoming acid. So that means I want to remove this acid. So what I do is I'll combine it and then I'll bring it back, make it into H2CO3. So this is the one way in which it will either add a little H plus or remove. Kind of like, say, for example, you are making a picture or a painting, a watercolor painting. Okay, so there you have this picture and you are supposed to put some blue here. Okay, so then you mix it in your palette and you are trying to add, and then when you mixed, it became so very dark, right? So then what do? You add a little bit of white to it and to lighten it, and then you realize, oh la la, it became too light. So then what do? You add a little bit of blue to it to make it dark. So think about it like that. Okay, so a rise in pH will decrease the H plus ions and the reaction will move towards the right. Okay, and H2CO3 will dissociate more and release more of H plus into the medium to balance out. It tries to bring the pH back to the original values. A decrease in pH will increase the H plus ions. That means the reaction moves back towards the left of the reaction to combine the HCO3 minus and the H plus to give more of H2CO3. Okay, this is like almost the last part of the chapter. There are two things that you need to understand when I'm talking about acid, and then biology and importance of water bodies and so on and so forth. So right now we have a very high concentration of carbon dioxide in the atmosphere. Why is that? Because of emissions and fossil fuel burn. So a lot of carbon dioxide is present in the atmosphere. What does it do? It combines with water. It forms H2CO3. And this H2CO3, then it's an acid, right? It dissociates into H and HCO3 minus. What happens is this H and the carbonate combine to form more of this, which means this carbonate is not available for calcium to form calcium carbonate. Why do you need calcium carbonate? Corals need calcium carbonate. That is their structure. Now, what is the importance of that? Think about it like this. Coral is sponge, which is a creature which also allows for spots or areas for algae to come and reside and photosynthesize. Once they do that, meaning it sort of allows for a platform for algae to come and live in its shell, or the coral, in its coral, okay, the hard substance. And once it photosynthesizes, meaning I have a producer in place. If I have a producer in place, then I will have the first consumer. Then I'll have the secondary consumer. Then I'll have the tertiary consumer. That means I can sustain a food chain. I can sustain life. what happens is, if the carbonate is taken out of the entire situation and kept in solution and in acid form, what happens is calcium just floats away and there is no calcium carbonate, hard calcium carbonate made. That means no life, no coral. Okay. Another way in which you understand this is with fossil fuel burn, you have lots of sulfates, nitrates, and carbon dioxide released into the air, which combine with water in the clouds and water bodies in the clouds for now, when they go up into the air and turn into sulfuric acid and nitric acid, and they fall down back into the earth as they precipitate down as rain, and this is acidic. And if it falls in water, it makes the water pH lower. If it falls in land, it changes the quality of the soil. If it falls in plants, it burns them. It gives them an acid burn. So, acid rain has severe consequences, and all of that is because of indiscriminate burning of fossil fuels. Okay, there you have the coral reef when coral was being formed the way it should be, when some of the coral is leached out and there is no coral at all and there is no life sustained at this stage, and all that calcium is in suspension, making it turbid and unclear. Think about that.